Hello everyone! I am so excited to share with you a workshop I recently gave on automatic temperature and pressure log interpretation using convolutional neural networks. That's a mouthful, so let me explain it in slightly simpler terms. We have temperature and pressure logs from a geothermal reservoir, and we would like to interpret 5 elements from these logs: the feed zone depth, the reservoir temperature, the pressure depth, and we are going to learn how to use a spatial type of neural network to automatically do this log interpretation. So what are we going to cover in this workshop? First, what are convolutional networks? Then, what is the problem we are trying to solve? Like I said, it's going to be related to well log interpretation. Then I'm going to practice doing a convolution. Then we're going to do a code practice, of doing like a convolutional neural network, but by hand. Just the simplest, without any gradient descent, just what is the innards of a convolutional neural network. Then we're going to take a break, and then learn what are the typical elements of a convolutional neural network architecture. And then we are going to learn how to use TensorFlow to go and implement a CNN for well log interpretation. This is a great workshop if you're doing research on this topic, or if you are working in the geosciences and would like to learn how to use CNNs for well log interpretation. So let us get going. We're going to go and have a lot of polls, kind of imitating the original workshop form of this from this YouTube tutorial. And so I highly recommend that you pause the video, answer the question in your mind, and then continue. So first question, what do you know about convolutional neural networks, otherwise known as CNNs? Now, what do we got people saying here? CNNs, you mean the news channel? So yes, guys, if you are in a tech talk and you hear CNN, do not fear. They have not gone to talk about, the news. This is a convolutional neural network. So, first lesson learned for today. Moving on, what is a convolutional neural network? These are the basis for computer vision. You always see these images of object recognition for self-driving cars. For example, here, out of a paper on the topic, we can kind of imagine someone walking or a car driving without a driver, looking around at this image, and they can then detect, is this a car? Is this an umbrella? Is this a person? And this is kind of one of the revolutionizing aspects of machine learning, this whole CNNs and computer vision. And we have here another example, a classic, what's called MNIST dataset, where we have the handwritten digits, and the task is to go and recognize what are these digits based on the image of them. Then you can use this, for example, for the mail system, try and recognize, your friend's terrible handwriting, etc. So the main takeaway here is convolutional neural networks are one of the cornerstones of the machine learning revolution that has been happening in recent years, together with natural language processing and other capabilities. So how does this relate to geosciences? CNNs can be used in 1D, 2D, and 3D geological and geophysical applications. So, for example, a 1D, what we have here, the temperature versus depth, and detecting different elements in the logs. Another example here is we have a seismic impedance cube, and we want to detect different geobodies inside this cube, so we can do that using convolutional neural networks. So, first thing to know about these networks is to understand that all images or time series, they're all basically numbers. And since they are numbers, we can manipulate them with mathematical operations and then get to a certain classification. Is this a cat? Is this a dog? Is this a hat? Is this a mug? All by manipulating these numbers that are the basis of the different images. So for example, one of my favorite birds, the dark-eyed junco, we can go and detect that this is a bird by multiplying the different numbers in the basis of the image by filters and other numbers, and then doing summations and taking the max. But basically, a series of very simple mathematical operations will allow us to go from this image to the prediction that this is indeed a bird. So some details about this. Whenever you hear the word convolution, it's a little scary, it's a bit long, it's hard to say, but all it means is a filter, right? Like on your phone, you take an image of something, you can put a filter, and then that image changes to something a little different. So for example here, if we take this input image and we go and convolve it or do a multiplication and summation operation, okay, then we can get this what's called a feature map, or the result of the convolution. So we take this image here, we take these values, and we multiply each one of these values by the values in the image, and then sum it, and then slide the filter over, multiply, sum, slide over, multiply, sum. And we can kind of see that also over here in this little GIF. I'm going to wait for it to restart again. We have here the kernel or the filter. We multiply the kernel by the image like we see over here. And then we take all these different multiplications and we sum them, get a value, and put it into this feature map or the output. So like we see over here, this is just an operation of multiplication and summation. That's it. That's it. Someone asks you, what is a convolutional neural network? It is multiplication and summation. That is the main element that is going on over here. Taking another example, let's say we have a car and we do several different types of filter on the car. Now, after we do the first round of filtering, it still looks kind of like a car, but different elements of the car are kind of highlighted. Now, ignoring the other operations here, we have a convolution followed by another one, by another one, by another one, by another one. And then in the end, we get a feature map, which doesn't exactly look like a car anymore, but which the neural network can then use to go and predict that this is indeed a car. So this is the basic elements of what is happening in a convolutional neural network. Now, do we need to go and find the values of these filters on ourselves, by ourselves, by hand? Like for example, over here, we have this filter, which is a series of 9 digits. Do we need to go and know these ahead of time? And the answer is no. That's the whole point of the convolutional neural network, is to find for you the best filters by using some variant of gradient descent. And we can see here different variants. And what these different optimizations are trying to do, if we're looking here at the loss space or different values of the difference between the label and the truth, between the label and the prediction, we're trying to find the lowest error or the lowest loss. And for that, we have the gradient descent moving and choosing different weights until it gets to find the lowest error, which for our case would be the lowest set of weights. Now, this is a bit complicated, so we're going to go and review this again, but just to give you kind of a heads up. And this is showing us different types of optimizations that are available inside a convolutional neural network. Okay, so right now we're going to go and talk about our specific scenario. What are we using CNNs for? What is our problem? So we're looking at a geothermal reservoir. That's the topic of the objective of the CNN that we're for this particular tutorial. We have a geothermal reservoir. What does that mean? We have cold water that goes from the mountains into the earth, and it gets heated up close to the magma heat source, and then it goes back up on top of these faults. Now, faults are these cracks in the ground which allow the water to move more freely. So in an area where there's also hot water and also a lot of cracks, you'll see the hot water go up the fault and then maybe cause some sort of conduction circle over here. And this is a great place to put a well and then to generate geothermal energy. And we'd like to detect that in the logs. Where is this reservoir located? So what will happen is that we'll have a logging truck and it'll put a sensor down the well. And as the sensor goes down the well, it's warming up, warmer, and it gets to these faults. And then suddenly it's much hotter because this fault is carrying hot water, and there's a lot of hot water kind of rotating over there in this convection circle. So it's going to go warmer, and hotter than usual. And then once it gets out of the reservoir, it'll go back to the background geothermal gradients. So we can see that over here, the temperature is increasing, and then it suddenly spikes up. And then we say, oh, this is the top of the reservoir where it spiked up, and then it's going to go and kind of stay hot. Sometimes this can even be a completely straight line, what we call a isothermal, or the same temperature section. And then it will go back to the background gradients. So when we do this interpretation, we have here this temperature and the pressure log, and a reservoir engineer has to typically interpret 5 elements. 1, where is the top feed zone, the bottom feed zone, the reservoir temperature, the reservoir pressure, which is the pressure in the middle of between the two feed zones, and also the depth of the reservoir pressure. So these are 5 elements that a reservoir engineer usually needs to interpret from the temperature and pressure logs. So we're going to go now back to the technical part, and we're going to learn about doing convolution by hand. So I kind of reviewed a convolution and tried to convince you that it was not a scary thing. So let us go and do it by hand. Nothing like doing it to alleviate any fear of it. So we have here a time series 153, and now we're going to do a convolution with a filter 0.5, 0.5. So how is this going to work? I'm going to take my time series, and then I'm going to put the filter right beneath it, and then I'm going to go and multiply and sum. So I can do 1 times 0.5 plus 5 times 0.5, and that will give me a value of 3. And then I'm going to go and put this value as the first value in my feature map. Then I'm going to slide the filter 1 over, 2 over here. And I'm going to have 5 times 0.5 plus 3 times 0.5 equals 4. And that is the second element of our feature map, or the result of the convolution. Excellent. So this is a convolution. That's it. We just did a convolution. Now you'll notice that we could have slided it perhaps one more, but in this scenario, we are not going to have any padding, so we are just going to leave it in this case. So it is time for your first exercise, guys. So I highly encourage you to pause in one moment and try to solve this yourself. And this is the question. What is the result of the convolution? 153, negative 1, 1. So please, guys, go at it. Okay, so I hope you just tried to do that by hand, and let us see what is the answer and what people have chosen. Great, so you see most people have got it correct. It is indeed 4, negative 2. And how do we know that? We do, the first one is 1 times negative 1, plus 5 times 1, that's 5. So that would be negative 5 minus 1, 4. So that's the first element of the result. And because that's the only option here that starts with 4, we can know that it is the second one. We don't even need to do any more. So that is great. You guys just did a convolution by hand, not difficult, multiplication and summation. So that is wonderful. Let us continue. Let us look at convolution. We have here a kernel, and this is exactly what we said, a filter, and it has this round shape over here. This is a smoothing kind of filter. It looks kind of a bell curve or a Gaussian filter. What we see here is kind of a noisy signal. You can see it become randoms, ups and downs. And once we're going to do filtering with this smoothing filter, we're going to see the result is going to be much smoother. So like we did here, we take the values of the filter and we multiply and sum, and this is the result down here that we get. And we indeed see that our feature map is much smoother. Great. So right now, I think you're ready to do a hands-on exercise, woohoo, with Google Colab. And what we're going to do is the first element of a convolutional neural network, but we're going to do it kind of by hand. By hand, not exactly, but with code. But we're just going to code up the convolutional neural network by ourselves, not using any fancy package. So for example here, I'm going to take the temperature log, and we're going to try to use a handmade convolutional neural network to predict the first feed zone. So please, guys, please go along in this workshop and open the first link of the Colab notebook that you should have in the bottom in the description. So, and just go to the description of the YouTube and click the first Colab notebook. And that will bring us over here to our convolution exercise. So let us get going. So the first thing that you gotta do is we're using Google Colab, and to run any code block, you click over here on the run cell. Another option that is kind of cool is to go click on your cell and then on Shift Enter, and that will run it for you as well. And like I said, our first goal is to detect the top feed zone using the different elements that are inside a convolutional neural network. So we're going to take this series of temperature values per depth and then predict the value of 1410, the top of the first feed zone. Now you're probably asking yourself, how can we do this? How can we go from a whole series of values to the value of 1410? Let's see how we can do it. So first thing first, let's learn about convolution using some basic code. So here we're going to use NumPy or numerical Python to solve this little example that we just did by hand. Let's see if it can do it by itself. And we see here the result, 4, -2. So that is exactly what we found by hand. So this is great. We no longer have to do these things by hand. We can use NumPy. Excellent. Next thing that we're going to do is look here at a two-dimensional convolution just to get more of an intuition about it. I'm going to run here the different parts of the code. And there we have here an image of a fault. And we're going to see if when we apply 2D filters, can we see different interesting elements inside this image. So here are our filters. You can see kind of fairly interesting ones. And let's see what happens when we do a convolution of the image with these filters. And wow, what we see over here is some of these filters really pop out with some of those faults. For example, over here, we can see the faults quite nicely. Also over here, in some ways, we can see the different layering. So we can already see how, convolutional neural networks or convolutions just on their own do a great job for edge detection, which we can also use for different problems in the geosciences that we're not even discussing really right now. So now it is your turn. It is time for an exercise. I want you to find the best filter for the temperature log. So if I go over here and I have my temperature log, let's say I run this filter, 010, over here on this temperature log. What I get is, as a result of the convolution, this the same input as temperature. That's because this is a terrible filter for our purpose. What I want you to do is to kind of play around with this filter values to go and try to find a filter that will make the top feed zone just pop out, just like that. So for example, if you go here and you can try to pick out, just random numbers, maybe here, -4, 1, 3, and then, oh, that's kind of nice. This is a pretty good one. So I want you to try to play around with these values and try to see if you can find a filter that will make this section pop up just perfectly. And I made the job a little bit easier for you. You can choose random numbers yourself. You can look at some of the examples here and be inspired to create a one-dimensional filter because we're working on basically one-dimensional data. And another option is I've given you here inside this next poll some different options that you can try out. So please try out these different filters and let me know what is the best filter for getting the feed zone location. So again, please pause your video, play around with the code, and then click play again on this YouTube video. So I hope you went and you tried different things out, and let's go and see what people chose. And look at that, we see a lot of people chose -0.5, 1, -0.5, and that is indeed my favorite. This one though is also pretty good, so that's kind of tricky because the answer is not, there's no one perfect answer. There are many answers which are definitely very suitable. So let's go and try out the answer that most people have chosen. I'm going to put here -0.5, 1, and -0.5. And that is awesome. Look how sharp it is. Look how nicely it points out this top feed zone. That is amazing. Woo! Yeah, good job, guys. Now you're probably looking at this result, the convolution, and thinking to yourself, well, if only I could get rid of this section over here and of that section over there. I mean, all those values, they're below 0, and I don't want them to be in my next stage. If only there was a function that would take all values that are below 0, make them into 0, and all values that are above 0, it would keep. And there, my friend, it already exists. It is called, presenting here, the ReLU, or the rectified linear unit, and it does exactly that. It takes values less than 0 and throws them out. Values that are more than 0, it keeps. So that is just this very basic function, NumPy maximum 0x, or it takes the value, and if it is 0 is higher than it, then it just gives it a value of 0, and if it is higher than 0, it will keep it. And let's see how that looks by clicking over here on the play button, and then Wow, the ReLU just did that. It got rid of all these values that we did not want. So we see here the temperature, the filter, the convolution, and then the ReLU on the convolution. Wow, that is wonderful. But now you're kind of thinking, oh, well, the value here is 0.5. How am I going to get to a depth of 1410? I mean, those are just different values. They're so far apart. If only I can multiply each one of these values by 0, multiply this one by around 2,800, and then sum it up. That would give me a nice close approximation for 1410. And guys, you do not need to invent anything new. It already exists. It's called the fully connected layer. This is one of the most important final elements for a convolutional neural networks. We have here, for example, this series that we would like to multiply. You can see the values here. I made this one, the peak, a little bit higher. Then we have some weights, weight 1, weight 2, weight 3. And each element here, we multiply by a certain weight. And then we get a new value, and then we sum it up, and we would like to then get a feed zone, get the feed zone depth of 1400. So you always see these lines, and you think, oh, it must be very complicated. Look at all the interconnected nodes, da 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 da. No, guys, it is just a multiplication of the elements by some sort of weight, and then a summation. Multiplication and summation, and that's all that is happening here. Of course, we do have some nonlinear things like the ReLU, which help us out, but in general, there's nothing to be scared of. Multiplication, summation, and a fairly simple concept of gradient descent, or some variant of it. So what I've done for you here is I made for you a weight. I have initialized these weights for you by 0. And what we want to do is to make all the weights 0 except for the weight at the peak, at which we would like to give a value of 2,800. So what I'd like you to do here is find the index of the peak and then put the number here. And then this will change the value of the weights at that index to 2,800. So right now I have here the default value which I gave, which is 195. And what we see here is we have the temperature, the filter, the convolution, the ReLU. And this is our weights, and then we have the weights times the ReLU, and then when we sum this up, we get a value of 126, which is not 1410. It's not what we want. So we want to find the index around this area, and then to use that inside of our weights. So I'm going to let you go and play around with changing this value until you can get 1410 as a result of the multiplication and summation. So I'm not going to leave you completely in the dark. I have made for you here some possibilities. So please go and check these out and look at different values, and let's see what you get. Okay, so I hope you paused and now tried it on your own. Let's go over here. And yes, we see almost everyone got it as 141 as the best index. So let us go back to our notebook and let's go, wrong one, and change this here to 141. Perfect. Go here, and voila! The sum of the weights times the ReLU of the convolution of the input is 1410. Oh my god, guys, we got it. We got the depth of the first feed zone by doing by hand a convolutional neural network. That is amazing. So to summarize, wow, look at what happened there. I didn't realize that's possible. Let us go and share here some final thoughts. Okay. It's hard to choose a filter and weight values by hand, right? And this is the whole point of a neural network in general, and that is that we can train it. What do I mean by training? Training means that the neural network can use a different optimization method to find for us the best filter and weight values. It will go and try different weight values until the difference between the label and your prediction is has the lowest error or the lowest loss value. Okay, so whenever someone says training a network, the network isn't going on a bicycle. It is just trying out different weights that make the most accurate predictions, right? So we have here what's called the forward propagation, and then to find the weights, it uses the gradient. So you have here the derivative of the loss with respect to the weights, and that is what helps the use of the gradient descent together with this architecture is what makes CNNs work. So that's awesome. We just did a CNN by hand. We know how the innards of a CNN works. That's great. And what we're going to do next is, we don't have to always do these by hand. We can use pre-existing packages like TensorFlow with a Keras interface. So give yourself a 5-minute break and let us come back and then learn how to implement this using TensorFlow. Isn't that exciting? With some code examples, so then you can use that for your research or for your work. Okay, so take a break and let's come back. Hello, everyone. I hope you took a nice 5-minute break. I took, as a matter of fact, a whole 1-day break, so I am all refreshed for this second section. And that's great because we are going to be playing around with some TensorFlow code. And that is great. So let us get started. So first thing first, actually, why don't you take the second link in the YouTube description and then go here into runtime and then click on run all, and that will run for you all of these codes for you, so you don't have to run each one by hand. Just go here into runtime and then run all. Great. So after you do that, let us go back to this presentation and let us get going. So another small thing is actually, I forgot to say, before you do the run all, you will have to first disable cookies. Now I know this sounds very sketchy. You don't have to do this. It will still run if you have the cookie blocker. But we are using a extension of Google Colab called TensorBoard. And even though TensorFlow and TensorBoard are managed by Google, it's still considered a third-party cookie. So for it to work, you will have to disable your cookie blocker just for this section, and then you can turn it back on. Now, if you don't want to, that's also fine. It will still run the basic things. It just won't have the output, which I'll show you soon, so you can decide if you want to after you see it. Great. So, before we get into the code, let us do some general overview. What is a typical process for implementing a CNN or a convolutional neural network model? First of all, and this always surprises people who are newbies in the area, data preparation is something like 95% of the work. Really, just getting the data in a nice and structured setting, finding all the data, making synthetic data, which is especially true for the geosciences, cleaning the data, taking out outliers. So this is, 95 or even more sometimes % of the work, okay? So the actual data science is only 5%, really. I mean, you could say that data science is about, data wrangling. It's also what data prep is sometimes called. Then we have some data exploration, attribute engineering, so making new attributes of the data, dividing into training, validation, testing, setting up a model architecture, training the model, and then doing some hyperparameter tuning. And I think we're going to do just about a little bit of all of these steps in this second part of the tutorial. So, data prep. The first step, and this is the most important, is to get sufficient data. Maybe in, if you're doing a random forest, if you only have 1,000 samples, you could probably get away with that. I mean, that's totally fine. But if you're doing a CNN or a neural network, you are needing to train a lot of weights. So you're probably going to need several thousands or more number of samples. So, for example, here, just to illustrate why, imagine when you want to train a linear model for these, 3 dots over here. So you could say, oh, this looks like enough. These are pretty straight dots, and you can draw a line here and say this is my model. And but though that if you have more dots, what if these dots were totally kind of anomalous? So you can, for training one weight or the 2 weights, W1 and W2 in a linear model, you probably need a solid 30 at least points to kind of say, oh, this is, a slightly robust model, assuming that, it's a Gaussian error situation, etc. But with small standard deviation. But I think a good rule of thumb that I've heard is that you should have at least 10 samples per weight that you are training. But just take that into consideration. If you are training a really heavy neural network and you have parameters and 1,000 samples, that's definitely not enough data, and you'll be for sure almost 100% overfitting. So yeah, get enough data is definitely the most important part of this. Typically, if you're doing other types of work, like for example, just image recognition, you can increase the data set by rotating, filtering, zooming. You can play around. So you can take one sample and turn it into 10 by doing some good pre-processing. But in geosciences, that can be kind of difficult. If you have, for example, well log data, you can increase it by subsampling, maybe taking sections of the well log. So there are also ways to augment your data set. But yeah, this is the most important part, get enough data. So the way we're doing it is I actually have a note but for this example, we're just going to use non-proprietary synthetic data completely. Also, this is just for educational purposes, so it's okay. So what I did is I made 3 different styles of temperature logs and automatically picked for them the top and the bottom feed zone and all the rest of the necessary parameters. So you can see one here that kind of looks with a completely straight isothermal section. This one here has several different sections to it, and this one is isothermal but never goes back to the background gradient of the temperature. So these are some synthetic data that I made, and we're going to see that soon in the code. Next step, it's always considered best practice to normalize the data before training, so that's subtracting the mean and dividing by the standard deviation. Then, another best practice is to divide into training, validation, and testing sets. So I think for us right here, we're mainly going to do just a training and testing set, but usually for hyperparameter tuning, you would have a training, and then you would use the validation set for hyperparameter tuning, and then you'll have a testing set. Okay, so for us, we do have 80% training, 10% validation, and 10% testing. Okay, we're also going to be doing some early stopping. So what happens when you train the model, you'll always be improving the training error, but at some point you might start overfitting and not improve your validation error anymore. At that point, you'll want to do early stopping, and that will make your model more generalizable and less overfitting. So we're going to be using that in our architecture. So if we look in general on the building blocks of a CNN, what do we have? So we have here a input layer. We have several convolution blocks, and we can kind of see this in this model over here. So we have a convolution plus ReLU. Guys, these are all things that we know and we did in the previous exercise. Then we have max pooling. We have a fully connected layer. Ding, 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 ding. That should ring a bell. And then we have a ReLU again. And we didn't talk about this because this is mainly for classification and we're doing a regression problem. But if you were doing a classification, you'd also have the softmax. The only one we didn't talk about yet is max pooling, and we'll be talking about it soon. So what you have here is you have a certain image, and it has RGB, so it will be a certain size, 224 by 224, and one layer for each color, red, green, blue. And then you will go and filter it multiple times. So for example, you could have 64 different filters and a valid type padding. And if you did that, you would end up with 224 by 224, 60 by 64 number of feature maps. And then from then, you can do over and over again different convolution blocks, convolution, max pooling, etc. until you get into the end prediction. So, we're going to practice soon right now looking at another architecture. So based on what I'm telling you, I'm going to give you a little quiz to check if we understood the different setups of the architecture. So we can see here blocks and different elements that we have inside the blocks. So let's see if we can try to understand what is going on over here. So please look at the question, how many blocks are there in this model, convolution blocks specifically, and how many filters are there in the second convolution block? Okay, so take your time, pause, and try to answer this question. Okay, so hopefully most people got the answer right. And so what do we have here? We have most people chose 3 convolution blocks and 16 filters in the second block. oh, this is actually the same one, so that's why it's kind of split over here. Oh, my mistake. But anyway, so yeah, so one thing to note is that inside these CNN architectures, sometimes you'll have blocks that look just about the same, and they have the same repeating elements in them, a convolution. Here there is something called the batch normalization, a ReLU, max pooling. And then again, another block with convolution, batch normalization, ReLU, max pooling, etc. And then in the end, a fully connected, and then a softmax, and then labeled. So what we see here is that there's 3 blocks that have the same structure. So I'll say there are 3 convolution blocks. And what we see here is that we have a 3x3 filter, and then we have 16 of those filters. That's this number over here, which leads us to 3 convolution blocks and 16 filters. So that's great. Now I hope you guys got a little bit better these diagrams, because sometimes they're scary, but we just did a little practice in reading these CNN architecture diagrams. Okay. Great. Now, I know when we did the convolution exercise, you were probably wondering, well, why did we stop sliding the filter when we got to the end? We could have slid it a little bit more, but we were missing some data, right? So when you get to these edges here for the convolution, you might think, oh, well, if only I had a way to pad it, or to add there some extra information. So if you were doing a full padding, yeah, you could add some zeros here on the other side, and then go all the way from side to side, and then your resulting convolution will be much larger. Another option, what we did previously, is called valid padding, where it only slides where it can be the filter and the signal completely overlap. And I think what's shown here is a same type padding, where there's a reflection of the signal across the area of the original signal. So you can see here it goes down, down, up, and here it goes, well, up, down, down. So that is just a reflection of the signal, and then this reflection allows us to filter and have the input signal and the output signal, or the output convolution or feature map, to be of the same length. So valid will give you the same output as input in terms of size. Okay, let's go and review max pooling layer. Let's say we have this in 2D, this image, and we do a 2x2 filter with a stride of 2. That means I go here and I have a 2x2 overlap. I say 1, 1, 5, 6, which is the largest. Oh, it's this, it's 6. And then I go and I put it over here. And then I go and I slide it over. And I say, okay, let's pool all the numbers together. Which one is the max, the maximum? And then I put it over here. It's 8. And here it's 3. And here's 4. Now, I'm going to give you a question in a minute to see if you understood this section. So note here that says a stride of 2, right? There was another option that I would actually only stride 1. I would go here and I'd say, oh, 1, 2, 6, 7, which one is the largest? And I would say 7. And that would give me a slightly different size for the end result. Okay, let's test your understanding. So what is the result of this max pooling? If I say to you here, 1, 5, 3, 2, and I wanted to do a max pooling with a 2x1 filter, so this is a one-dimensional pooling. So the filter is just 2x1 and a stride of 1, and I'm doing no padding. What would be the result? So please pause, take a look, think about it. Okay, I hope you thought about it, and let's go and look what the answer is. And let's see if most people got it right. I think that is true. So let's kind of think about it ourselves. I slide it 1 and 5. Which one is the largest? 5, and I put it over here. Great. Then I go here and I say 5 and 3, and I say which one's the largest, and it's 5. Oh, I think most people got it wrong actually. And then I get 5 again, and then I'm going to slide it one more time, 3 and 2, and I get 3. So 5, 5, 3. Okay, so this is a little bit tricky because it's a little different than the previous example, but the second half of the people got it right, so that's great. Let us continue. Flattening. Now, you probably ask yourself, how do I go from that 2D situation into a 1D situation? Well, I just do flattening, right? So I had here 6, 8, 4, 7, and now it is one long vector and no longer two-dimensional. That's just how simple as it is. Dropout. So again, to go and alleviate the problem of overfitting, one of the techniques is called dropout, where we stochastically remove some nodes from the model, so the model is not too dependent on single weights or single features. So again, this is another form of what we call regularization. And we're going to be using this as an option inside our CNN architecture. Another option is called batch normalization. So remember we said previously that standardizing your input data is a good idea, but another good idea is to actually standardize also, if you think about it, if we just kind of ignore the input data, even the first hidden layer, it can be some form of an input and then an output, right? So why not, if we standardize the input data, why not standardize also the different outputs from the hidden layers? So that is what batch normalization does. It standardizes the data, and this, I don't know if there's like a proof of it, but this has been shown to improve the convergence for CNNs and neural networks. Okay, then we have the learning rate and the decay term for the learning rate. So you can think about it like when you take a gradient, if you take small steps each time, then you will very, very, very slowly get to your minimum of the loss. If you go too fast, you might jump over, so to speak, the area of the low point. So the best kind of learning rate is learning rate that starts high. So you, when you have very high loss, then you have large steps, and when you get closer towards small errors, then you will slow down your learning, so you can just kind of like perfect your weights. So you have a learning rate that kind of changes with the time, and you have a term for that. Okay, so what kind of architecture are we going to use and look at inside of our Google Colab notebooks in one moment? What we have is we have our input. We have 3 logs: the temperature, pressure, and we can do some attribute engineering and add a temperature derivative as well. Then we have an initial convolution block with an optional batch normalization, one of the activation options, an optional max pooling, and an optional dropout. Then, well, theoretically, we could say combine these convolution blocks together as one kind of form. Technically speaking, it's slightly more difficult because the way the code is set up. The first convolution block is a little different because the input that it's getting is a little different than the middle convolution blocks. But the middle convolution blocks are basically exactly the same as the initial convolution block. Then we're going to do some flattening, and then a fully connected layer to the output. And our output are these 5 elements that we are interested in: the depth of the first feed zone, the depth of the second feed zone, the reservoir temperature, the reservoir pressure, and the depth of the reservoir pressure. Great. So first, actually, one last thing before I go look at the code, and that is regarding hyperparameter tuning. So you're probably asking yourself, well, how do I know there are a lot of different architectures? How can I choose the best architecture, or the best number of convolution blocks, or the best number, what type of padding is the best for the convolution? So one thing that you would do is you would do hyperparameter tuning. And what that means is that you're going to try out a lot of different hyperparameters. You might go about it with some sense, maybe with some Bayesian optimization, but you can also just try out random different parameter options and see which one performs best. For example, over here, we have what's called TensorBoard, and this is the one that I asked you to disable your cookies for, which kind of helps you visualize hyperparameter tuning. So we have is different runs, and here they're actually looking at accuracy. So we're trying to get the highest accuracy, and each run has different accuracy. Each run also has different hyperparameters. So if we go here and we look at the hyperparameters tab, we can see the number of neurons, the dropout rate, the optimizer, and then the resulting accuracy. So this is kind of a TensorFlow demo. And we see how when they change different parameters, so here it's 64, here the dropout rate's a little bit different, and then they're trying out the stochastic gradient descent versus atom optimizer, and then they have different accuracy levels. And TensorBoard helps you go here, for example, into the parallel coordinates plot, and you can see, oh wow, look at this. The accuracy is pretty high over here. And what kind of parameters led to these high accuracies shown here in red. And this is kind of sometimes be a confusing plot. We can see, wow, most of the red ones seem to have the atom optimizer. And then we can say, okay, the red ones here also have a dropout rate, I think, tends to be fairly low, 0.10 to 0.20. Now, it doesn't drop out too many of its neurons at every batch. And then we can see also that the worst ones had a stochastic gradient descent and had a high level of dropout and a low number of neurons. So it's kind of cool. I think parallel coordinate plots are the best, really. And then what we have is a slightly more familiar kind of plot, the scatter plot. And we can see that over here. The easiest one to see is that, yeah, indeed, stochastic gradient descent has the lowest accuracy, and Adam has the highest accuracy. So this is just to show you a little bit more intuition about hyperparameter tuning. And now I think we are ready to go into the code. So hopefully your code ran. I think there was some error there in the bottom. That's okay. So I'm going to go to the top over here. Okay, so it says load function for creating 3 temperature log scenarios. So this thing here is where this block is where we create the different scenarios of the temperature and pressure logs. So you can kind of take a look at it, but we're not going to really review it here. You can see I randomly create a nice subset of different temperature and pressure logs. It says, congrats, you loaded the function to memory. And then we're going to call the function and create 30,000 training samples. Over here, we're going to do some attribute engineering. So we added the derivative to the data. So we had temperature and pressure that we had synthetic data for, and then we added the derivative. Why? Because the derivative is probably going to be extremely useful. And we can see that over here, where we plot the training data and the new attribute, the derivative of the temperature data. So let's take a look at some of these. So we have your temperature. The temperature derivative kind of looks interesting. Definitely a good addition for the model and will be useful for the CNN. And then reservoir pressure. You can see all these randomly generated temperature logs, which will help us to train our model. Great. Here we are normalizing the input data. Nice. And dividing the data into training, validation, and testing. So we have here 0.8 for the train, 0.1 for the validation, and 0.1 for the testing. Great. And now we're going to train the model. And before we do so, we're going to download a lot of packages. Okay, so now you've finished loading those packages. Great. And finally, here is where the architecture for our CNN is. So take good note. This is the important section. So the way the overall structure is looking is inside here, inside build model. We have a sequential model. Then, like I said, we have first a convolution block. Then for I, in range of the number of blocks that we decide, we create more and more convolution blocks. And then we have a final block. Okay, now let's take a closer look at these different types of blocks. The first convolution block, and look how simple the syntax here is. Just model.add convolution, and then we have here some options for the filter. How many filters do we want? What is the kernel size? So the kernel size is just because we're in 1D, the length of your filter, the length of your kernel. What type of padding we want? So is it full? Is it valid? I forgot for a moment what the other option was. And then we have here the input shape. So this is why this first convolution block is a little bit different, because it has this input shape parameter. Then if we want, we can optionally add a batch norm. Then we can add some type of activation function. And what params here is a dictionary that we're providing this model so that we can easily change the different values for the structure. So we keep the general architecture, but we're able to easily vary it around. Then if we want, we add a max pooling. We have a size for the max pooling. Remember, we just did one that had a filter that was 2 by 1, right? So here we'd write 2 if we wanted to replicate that. Then we have padding also for the max pooling, because the max pooling also can either go off the edge or not, as you would like. And I'm not actually sure about the, if you have a multi-dimensional situation, I'm not actually sure anymore what that is. You'll have to look it up yourself. Then we have a optional dropout. Great. So this convolution block is basically the same, except it doesn't have the input shape. Which is why it's here in kind of a separate section, but it's basically exactly the same as previously. Then as a finishing block, we have a flattening and a dense, fully connected layer. So all the things that we just reviewed in the slideshow previously, we have it all over here. Okay, so now here we kind of set all those hyperparameters, and you can see here, oh, here it's called same. So you have valid and same, it's different padding options. We have for activation, so if you're, we only talked about the ReLU, but actually some other activation functions are called the sigmoid and the tan H, which you could also choose. We have a different learning rate, the number of convolution blocks that we would like to have, so that's how many repeating number of blocks we would like as part of the architecture. So just to remind you a little bit about the format. Okay, let's see, it's over here. Oh, having some trouble finding it. Okay, there we go, it was just one slide prior. So we're going to repeat this convolution block multiple times. So that is what the number of convolution blocks is. And we have the number of filters, the max pooling size. So all these are the hyperparameters that I set. And now to create the model, I do here build model, giving it the parameters. I set up an atom optimizer. Of course, you can also vary this by slightly tweaking the code and have different types of optimizers. I set up what the loss is and also the fact that I want to track the mean absolute error. Now, absolute error is not something you can have as a loss because it's not differentiable, but you can still track it as a metric. And here this is a great function, model.summary, shows you all your different layers and most importantly, shows you how many different parameters you're training. So we see here we're training 3,000 parameters, we have 30,000 samples, so I think it should be enough. Now we're going to run the model. Now actually I did this a little more complicated. We're looping here actually over 4 options of values for the number of convolution blocks. Okay, so it's going to try a different number of middle blocks, 0, 1, 2, 3, and 4, 0, 1, 2, and 3, and then see what gives us, like previously in the hyperparameter tuning that I showed you, we're going to see which one gives us the best results. So you can see it running, and when it will run, it will show you this great live results, and then you can plot the error. So for here, the kind of converged fairly quickly in terms of training and validation. You can see the validation is a bit higher than the training error. And then we can see over here the same TensorBoard, but this time with our model. And I'm going to give you a little quiz right now. I'm going to kind of set you loose here, and I'm going to ask you, dum 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 dum. Let's present. How many, so I'm just challenging you to go and look there and see how many convolution blocks produce the lowest metrics validation mean absolute error. So please go to the TensorBoard, look at that hyperparameters tab, and tell me how many number of convolution blocks produce the lowest metrics validation mean absolute error. Okay? Well, I hope you took a look at that. Let's go and look at it ourselves. Right now, I can go into hyperparameters over here, and I'm going to see, okay, I have the different number of blocks, and I have the different validation mean absolute error, and it's looking over here that this last one, 3 blocks, have the best performance. And I can also see that if I go into the scatter plot. Oh, also sometimes this can be kind of messy, so let's actually just uncheck some of these that we only have our metric of interest, and then we go here to number of convolution blocks, and I can see, okay, so the worst error was over here with 0, then 1 was better, 2 for some reason randomly was actually worse, and then the best was with 3 convolution blocks. Now this might be a little bit different for you. This is a random process, and I think I only ran it for several iterations, so you might find it a little bit different for you. 2 might be better, rarely 1 might be better, but I think in general 2 or 3 blocks should produce the best results for you. Okay, now we're going to evaluate the results on the testing set. So this was evaluated on the validation, and now we're going to evaluate on the testing set. This is all pre-run, so that's why I'm not in particular running each one. And let's see what it looks like. So let's go here to the top. We're saying the testing mean absolute error is 8.6, so it's pretty similar to the validation. And this is what it looks like. It means that on average it's around 8 off from the results. You see this is 112 true temperature, and the predicted is 108. So on average, even though here it's 4.1, I think an average is going to be 8. So that's actually not that bad if you look at it. I mean, as a first run, we barely did any tuning. It's already looking pretty good on this testing set. And the truth is this can actually go down to 0 if you did some good training. So you are hereby challenged. That's awesome. Look at this. Pretty nice results. Do you see it? You just did some very basic training, and on your first run, it looks pretty nice, I'd say. Now let's go and take a look, because previously we found our own filters. Let's see what the CNN, what kind of filters it found. So first we're going to go and print out what convolution filters were available. And now let's take a look at them. So this is if we just visualize them with colors. This is what 6 of the first filters look like. And then we can plot it in a similar way to what we did prior. And we have here the temperature, the way the filter looks, and the resulting feature map. So we can see that some of these maybe are a little helpful, maybe not. Maybe the ones that you found were actually better, actually. And you can see here, maybe this one is kind of helping to point out that zone over there. So you can see maybe this model needs a little more training, actually. Or here, it kind of peaks a little bit close to there, so try to find and see some meaning. Maybe we need a shorter filter. Maybe this was too long of a filter. Okay, so this is going to be the last activity for this tutorial. What I'm going to ask of you is to kind of doing a little competition here. I'm going to run it on YouTube. So I'm going to ask you to play around with the hyperparameters and try to get the smallest validation error. And the way you can do that is that you can mainly leave these alone, and then try to change around these parameters over here and see which one gives you the lowest mean validation error. Okay, so go here. I'm just going to give you one example. Let's say I change this to 2, and then I make the number of filters to 10, and I want to make our kernel shorter. So just change around and try to see what happens. And then very important is once you change it, you have to click here and run, okay? Otherwise, the parameters won't change and they'll stay the same. Then you go here and you click on play again, run. So I'm just showing you an example of how you could practice. And this will show you what the model looks like. And then it's running. Awesome. Running, and now here I ran it only for 10 epochs. So you can actually also change that right over here if you want it to run a little longer. See if you get any better. Okay. And if you're wondering where are all these models being stored here on this Google Colab space, so you can just go over here while it's running. I might as well show you another cool thing. You can see that all the training data kind of printed out over here, and here we have these are the blocks, the best models saved in the .h5 over here, so you can actually load them again and use them. And then I think these models are actually going to be called My Run, right? I think I gave them that name, My Run. And then we can load those as well. And let's see what's happening. Okay, now we're looking at our different laws for the different run. Great. Awesome. And now I see why there wasn't an error. Then you go and you want to play around. So right now you see we made 2 runs. One was the default, whatever was there. And we can go and check out the testing error of these different runs. So I'm going to go here and I'm going to do run number 1, and it loads it in. And then it tells me, look, it was actually 11, so that's worse even than the previous random one that we made. Now I'm going to go here and write 2, and then I'm going to load this model over here, my run 2. And wow, that was so much better. It's at 4. I just went from the previously, I had it at 11, then 8, and now 4. This is so much better. And now we can go and we have like a meta testing unit. So this is not something you trained on, and it's not something that you did for testing. and it just allows you guys to go and see how do you perform based on a constant set that everyone on YouTube has the same exact set. So you go here and you run this, and it's going to load that data set. Loading, and then you're going to change here to my best model, so that will be 2, and let's see what we get on the testing set, and it is 4.7, woo, great, and now you can take this number, and I highly encourage you guys to put your best result into the YouTube comments. Okay, you guys are hereby challenged. So I think that's it. This is, let's quickly go over what we did. We went and we created a CNN model. We have here the input temperature, we had initial blocks, we had a middle convolution, flattening, fully connected, and we did some hyperparameter tuning. We did a lot of stuff that are part of what it takes to make a CNN model. So that is awesome. Okay, so I think actually we even had as, let's see what we had during the workshop as the results for the competition. Seems like it's not actually showing. So that's, oh, there it is. We see here people got, so we have some 4.6, 10.6, 4.0, which was the best score, I think 4.2. So you guys, you can compete with what people did in the workshop. Great. So it's just some insights from this particular problem that I previously ran. The number of convolutional blocks is one of the most important hyperparameter tuning parameters. So we see over here that 3 convolution, that it has the highest sensitivity. Then the padding type, whether it's valid or same, has the second level importance. So you can do sensitivity analysis and see which hyperparameters are the loss is sensitive to which hyperparameters. So that's a great exercise that you can also do and try to get some insight out what hyperparameters are most important for you for this problem, and then you can focus only on those if you would like. So we can see here, for example, that the error when you have more and more convolution blocks goes down. Now this will probably plateau, but we can see that overall you can get pretty close to 0 with a validation mean absolute error. This is normalized, but still even in absolute numbers can get pretty low. Okay, what else? Another kind of variation on this is that you can have the temperature of depth, and let's say you don't want to give one prediction as a result. So you can give multiple predictions, like your top 5, and then you allow the user to decide what is the best pick for them. You don't have to give only one result. This is kind of like imagine you're doing well log picking. Sometimes it's best to leave it to the geologist or reservoir engineer to do the final pick, but it's still very helpful to give them some suggestions. And the way this is done is it's kind of turns this into a 200 parameter classification problem, where the classification is it 200, 199? What's the index of the first feed zone? And then you get a probability for each point. What is the likelihood that this is feed zone? You choose the places of the top 5 likelihood, but with also some spacing restriction. So that is one way that you can turn this into a more usable kind of application. So some future work, because this was related mainly to geothermal, future work for geothermal applications using CNNs could be for multi-log interpretations where we have temperature, pressure, perhaps more logs. And then some potential data interpretation, so potential fields such as gravity, magnetic, or also seismic data interpretation. Okay, I think that is all we have. Thank you so much, everyone. If you have any questions, please leave them in the comments. And thank you very much for listening. I hope you successfully managed to implement your own CNNs and that this tutorial was useful for you. Have a great day.